Welcome to the video for Lecture 16, Section 1. This video is an introduction to stress-strain relations in preparation for the next video on strain gauges. Strain gauges are an important sensor and one of the few that you can see entirely. You will mount strain gauges for one of the labs, so you will get to work with them intimately. As you would expect, a strain gauge is used to measure strain. Strain gauges are also used in several other sensors, including load cells, pressure sensors, and torque sensors. Since strain gauges are used in so many other sensors, it seems important that you learn about strain gauges. If you are familiar with the basic stress-strain equation, Young's modulus of elasticity, Poisson's ratio, and Hooke's law, you can stop listening to this video and go to the next one. If you want a review, keep listening. Strain is defined as a change in length per unit of initial member length. Strain can be either tensile, where the member becomes longer and thinner, or it can be compressive, where the member becomes shorter and thicker. Strain, commonly described by the lowercase epsilon, is defined as the change in length, delta L, over the initial member length, L. Strain has units of length over length, millimeter per millimeter. Stress is defined as the force per unit area applied to a member. Stress is usually not measured. We will measure strain and calculate stress using Young's modulus of elasticity. Stress is commonly described using the lowercase sigma symbol, and stress equals the force per unit area. The relation between stress and strain is given by Young's modulus of elasticity and is described by a capital E. The ratio is stress over strain, or sigma over epsilon. And after some manipulation, Young's modulus of elasticity, E, equals the initial member length times the force divided by the change in length and area. The units are commonly given as gigapascals, and which is pascals times 10 to the 9th power. If you look at the stress-strain graph, Young's modulus of elasticity applies only along the linear part of the response at low strain levels. This relation does not apply if you reach the yield strength of the material, after which the material does not return to its original shape. Another relation that we need to use with strain gauges is Poisson's ratio, given by lowercase mu. Poisson's ratio relates a change in the horizontal strain to a change in the longitudinal strain. So if you take a vertical bar and compress it, the bar needs get far fatter or thicker as it gets shorter. The change in the horizontal or lateral strain divided by the longitudinal strain equals mu. Mu is constant for most materials. The last relation we need to know is Hooke's law. Hooke's law describes the proportional relation between the directional stress and the directional strain. For one-dimensional problems, also called uniaxial problems, Hooke's law is the same relation as that given by Young's modulus of elasticity. So in one dimension, sigma x equals E times epsilon x. Remember that we said the stress is usually calculated using the measured strain. Strain gauges are used to measure the strain, and we calculate the stress. For stress in two dimensions, biaxial problem, Hooke's law has two equations for finding the stress sigma in the direction of the principal stress x and the stress sigma perpendicular to the principal stress. The equation includes Poisson's ratio mu. There are more equations for finding stress in all three dimensions. Again, if you want to calculate stress in all three dimensions, you will need to measure stress in the three directions. One other relation is used when working with strain gauges. The relation shown describes how much strain is generated by a temperature change. Many materials expand if heated or contract if cooled. The temperature coefficient of a linear expansion alpha is equal to the strain divided by the change in temperature. We will use this relation to estimate the strain error due to self-heating when strain gauges are powered. Strain is a change in length per unit length. Strain gauges are used to measure the change in length per unit initial length. After we measure the strain, we calculate the stress using the appropriate Hooke's law equation, Young's modulus of elasticity, and Poisson's ratio. This brings to the end of Lecture 16, Section 1 video. The next video will cover strain gauges in more detail. Please write down any questions you have and bring them to class or lab. Thank you.